Hi guys, welcome back and welcome to my YouTube channel, Electronic and CNC Lab. In today's video we will see what a breadboard is, what it looks like and how to use it. Let's say right away that a breadboard, also known as a waffle, is a tool used to create prototypes of electrical and electronic circuits. But how many of you know why the breadboard is called that? You must know that in the early days of electronics, electronic engineers, and not only them, pushed nails into breadboards, literally the wooden boards on which bread is cut, also known as cutting boards. They would then connect and solder electronic components and electrical wires to the nails to create their circuits. Here is an image taken from the makeeasin.com website since a few decades. However, breadboards are no longer made with wooden boards, nails and a hammer, but are constructed from plastic plates drilled horizontally and vertically with a pitch of 1/10 of an inch, or 2.54 mm, which is also the pitch between the pins of through-hole integrated circuits. Underneath the insulating plate are contact strips that elastically close at the sides to facilitate electrical contact. The breadboard is an essential component for making, for all peers, the two electronic circuits because it requires no soldering and is convenient and quick to use. Pass me the comparison, it is a kind of Lego but in the field of electronics. Let us now see what is inside a breadboard. To give you a better idea, but also out of curiosity, I have opened up a breadboard so that you can see and better understand what it looks like inside. So, as we can see, the typical breadboard is formed more or less like this. So, you usually find the ends of the bushings, which are these colored connectors where we can insert banana plugs, usually used to supply power to our circuits. Each of these bushings is connected to these two holes, as we can see from this picture. So, usually, the colors also identify the type of signal or voltage. In this case, the red bushing is for positive voltages, the black bushing for ground, the others for other types of voltage. If, on the other hand, our circuit has a dual supply, i.e. with a supply between minus and plus V, i.e. with two identical voltages but of opposite sign, then we choose by convention to use the black bushing for the negative voltage, the red bushing for the positive, and the green bushing for ground. But let us now see how the supply voltages can be connected to the various tracks. So, here we see that there are black and red lines identifying the various grounds and voltages. We have 4 red lines, V1, V2, V3, and V4, which we also see here, which identify 4 supply voltages which connect to the yellow, blue, green, and red sockets. And then we have the black lines which are formed by an uninterrupted strip, from one end of the breadboard to the other, both above and below, used for the ground connections. All other holes on the breadboard are formed by shorter strips which connect the holes together in a horizontal direction. Finally, we have here at the bottom another 30 horizontal holes by 6 vertical holes, which allow us to connect further components to our breadboard. Finally, to see even better what the connections of these metal plates look like on the inside, I wanted to lift one of them up. And basically what happens? There is this curved tab that goes to the bottom of the bushing contact. Instead, the little springy tabs that close inwards are the ones that give us the electrical contact of the components that insert the holes, which go right in between the two tabs. Over time, however, as I said before, these lamellae tend to expand a bit and the contacts get worse. Or they can, if kept in very humid environments, also oxidize and ruin the electrical connections a bit. Let us now see, first of all, which cables are most suitable for connecting the components of our prototypes. There are 3 types. The first, and certainly the cheapest, is the single-core cable, also known as solid core or rigid cable. It is sold in reels of various lengths and many colors. The recommended wire size is 22 AWG, which is 0.64 mm in diameter. The color coding of signal cables can also help keep our circuit in order and distinguish power, ground, and various signals. The second type of cable is pre-cut jumpers. Many breadboards are often sold with assortments of pre-cut and bent wires. Last but not least, we have the male jumpers, which consist of multi-stranded cables, i.e. flexible, but with rigid terminations at the ends. On the other hand, the cables I do not recommend for breadboard connections are the following. First, the multi-stranded cables, because when you insert them into the holes, the strands bend back there and give false contacts. Then there are the thinner cables, which are also more fragile. Finally, enameled cables, because they are often difficult to strip and tend to break more easily. Let's now see what the limitations of breadboards are, because obviously we cannot use them in any kind of circuit. Let us say right away that the breadboard is not suitable for every type of work. In fact, it should not be used in high voltage circuits. Therefore, avoid sending the voltage from your home socket into the holes of the breadboard. Another limitation is that, after many uses, the holes in the breadboard expand and the components do not make good contact. After a while, the plates inside the breadboard are likely to expand, thus creating false connections between the breadboard and the component pin. Another situation where it is not advisable to use the breadboard is with high-frequency circuits. I am referring to circuits with frequencies above 10 MHz. This is because breadboards have parasitic capacitances of between 2 and 25 picofarads per contact point, and there are also high inductances due to the length of the tracks. To summarize what has been said so far, I have prepared a small schematic of an operational amplifier, in this case the TL081. This here is a schematic of an inverting operational amplifier with unity gain. I have labeled the resistor R1, the feedback resistor R2, and the two filter capacitors on the positive and negative supply. We now move on to the connections on the breadboard. So I labeled the three sockets, the black one with the minus VCC, which is the negative supply voltage, the red one with the positive VCC, the positive supply voltage, and the green socket for ground. I first jumpered this hole with the V1 line, which will become my negative supply voltage. Similarly, on the red bushing I connected one of the two holes with the V2 line, which becomes my VCC+. Finally, the green bushing I connected it with the black line, which is our ground. So, as a first connection I connected the VCC+, then with the red jumper I connected the V2 line, which is a continuous line of pins all connected to each other with pin number 7. In the integrated circuits the pins are counted starting from this little connector that is perhaps not very visible, and counting counterclockwise you go to the pin on the opposite side. So we have 1, 2, 3, 4, 5, 6 and 7. So we have connected the VCC+ line to pin 7. In the same way, by connecting a second jumper with a black wire, I connected pin 4 of the integrated, so 1, 2, 3 and 4, the power line is negative. Then I connected pin 3 to ground, and here we have pin 3 of the integrated circuit, which goes on this line and connects to the breadboard ground. I then connected R1, which we have here. Here we have a line of pins connected to each other, as you can also see here, the various bars, and it goes directly to pin 2, and the resistor R2 connects between pin 2 and pin 6, so we have the resistor R2. The jumper from this line goes to the line of pin 2 of the integrated, and on the opposite side we have this other jumper that goes to pin number 6 of the integrated. Then we have these two capacitors, which are C1 and C2. These are filter capacitors that are put on all the ICs and are connected between the power supply and ground. In this case we have that pin 4 is connected to the negative supply, and through this connection it connects to ground. Similarly, pin number 7 of the integrated circuit connects to the capacitor, and on the opposite side to the capacitor it connects to ground. Finally, we have the two input and output connections. As this is an amplifier, it has an input BNC connector and an output BNC connector. To the BNC connector I connected a cable that goes to the line that goes to R1, and here it is, and the other connection, the green connection, is the ground connection. On the output we have the output BNC marked out, which connects to pin 6, and here is this line which connects directly to pin 6 of the integrated circuit. With this example we have completed all the connections and have done a bit of a review of how to make a circuit on a breadboard. One piece of advice I give is to use colors that are recognizable to anyone who gets their hands on the circuit. In this case, the supplies must always be clearly visible and maintain the same color throughout the circuit. As can be seen here, the red positive VCC is then connected with a second jumper of the same color as the black negative VCC continues in the same color to the integrated circuit. The same goes for all the ground connections, which in this case, since we have a dual power supply, I made with green jumpers and they are all the same color, while all the other connections in this case I made with a blue cable with a blue jumper, and we have them all here. Finally, let's look at two examples, one with these two screens where the circuit is neatly made and therefore works, and finally the last one which will definitely never work. Well, at this point I'd say we're done, and if you liked the video remember to leave me a like and subscribe to my channel. But if you want to receive automatic alerts every time I upload a video, also click on the little bell. I'll say goodbye now and see you at the next one. Bye and have fun.